Happy Friday. We have come to the last couple of lectures of the class. And in the last lecture, I started problem 1313 in the book, which gives us a very comprehensive overview of what we learned about creep and helps us to sort out whether we have a fatigue-dominated or a creep-dominated problem, even though we're analyzing it as a combined problem. And so we got about halfway through that. And so I'm going to finish that up today. This is just a slide that has the problem statement on it. And so we're working with the turbine blade in the high pressure stage of an aircraft gas turbine engine. And it had cyclic loading and also elevated temperature. It told us that at a critical area, there are 4 power settings. And each one was associated with a distinct stress and temperature. And so we were tasked with first determining the fatigue life, not considering any creep. And so we used the techniques from chapter 7, chapter 8 to do that, and we got 900 missions. And then we switched to thinking about creep only outside of fatigue. And so we used the techniques of this chapter, chapter 13, to calculate that we would be able to get about 595 missions if we only consider kind of a cumulative life model, trying to avoid stress rupture due to creep. So I'm going to write avoid stress rupture from creep. And we talked a little bit about how to combine those two effects. And what we did was take the Goodman equation, which is usually used for handling fatigue when you have non-zero mean stresses. And instead of the ultimate strength, we substituted in a strain-limited critical stress. So that was sigma CR. And at high temperatures, such as the ones that we're dealing with in this problem, we determined that the elliptic relationship might be a little bit more accurate. So part C of this problem, we're going to start there, says using the elliptic relationship, determine the life under combined creep and fatigue. And so we are going to do that. And then I'll make some comments on the ways that we chose to calculate the life so far. And then we'll spend some time on this part D. Does fatigue or stress rupture appear to be the dominant influence in this design environment? Okay. So this was the typical mission profile, where each power setting, we switched back and forth between them in this sort of a mode. And it gives us the time at each mode. So we use the time to calculate our lifetime in the absence of fatigue. And then we also did the rain flow style counting on here to calculate the remaining lifetime emissions, only with that in mind. So that was kind of our starting point. And so let's move forward now and talk about the combined situation. And we'll see if this material, which we were not told the exact material, has a synergistic effect of these two things, and if so, how? So the elliptic rule that we came up with last time, or the elliptical model, said that the amplitude of stress divided by the fatigue strength, sigma n, square that term, plus the mean stress divided by the strain-limited stress here, creep stress, square that. And we said if that was greater than or equal to 1, we would expect a failure. We didn't say exactly which of these two we would expect a failure from, but what we're going to do to interpret at the end of this section is we're going to look at the magnitude of each term compared to the other one, right? And so the first term here is focused on the high cycle fatigue, right? Because we have the fatigue strength, sigma n, and we have the stress amplitude, which is our understanding of high cycle fatigue, right? So, come on, pen. Okay, fatigue. If the first term is much bigger than the second one, we would say clearly this is dominated by a fatigue behavior. If the second term dominates, that's more of the creep behavior, right? So all we have to do is compare the magnitudes of these to see which one more dominates this situation. Okay, so that's kind of a hint, a preview as to what we're going to do at the very end. So if we look at this equation and we want to apply it to the situation that we have, we'll notice that it has amplitude, fatigue strength, mean stress, and the I'm going to call it a creep stress because it has a long name. So for each of the power levels, we identified a stress situation that was characterized by the amplitude and the mean. So we have those. We calculated those last time. So I'm just going to write them down here on this chart to start out. So I'm going to start with the max power, which had our maximum amplitude. So the mean, I'll write down the mean and the amplitude for each regime just to recall what we did last time. So the mean here was 28. These are all in KSI. And the amplitude was also 28. So those are highest amplitude. And there was only one cycle at that. And the amount of minutes that it was at that top max power situation is 31 minutes. Just going to write time, 31. Okay, and I'm going to do something here for this analysis, which is we have one equation, but we have 4 stress regimes, and we have also 4 power settings. And those are not exactly equivalent. So when we talk about fatigue, we talk about these reversed cycles. Well, those reverse cycles happen between 2 of these power settings. So we don't have a way of exactly matching in time the fatigue component of it and the creep, right? Because fatigue is n, it's number of cycles up and down. Creep is time, right? And so because I can't specifically put those together, what I'm going to do is I'm going to say generally that at max power, this is going to describe the stress situation. And then generally when we're there, this is going to be the time that is experienced at that setting, okay? This doesn't exactly correlate, right, each power setting, because our, even though I've ordered them in terms of like decreasing amplitude, that doesn't correspond specifically with each power setting. It just corresponds with the number of cycles we counted, right? And so there's no great way to assign those 2 totally different approaches to match up. But in this problem, it happens to sort of align. So that's what we're going to do here. So the next segment, or the next power setting, was cruise. So I'm kind of going to note that for that one, we had a mean stress of 43, amplitude 13, we had 1 cycle, and we had sort of 12 minutes at that power setting. For the flight idle, if we take and say that's kind of our third one down, we had a mean of 46, amplitude 10, we had 5 reversing cycles at that setting, and the time was 20 minutes. And then we had a ground, sort of a ground idle. And that had mean 43, amplitude 7, 1 cycle, and time was, nope, yes, 7 also. And I realize now that I've ordered these, and I could have put them in a slightly different order, right? Based on, let's say, maximum stress in each one, right? Or mean stress. I could have ordered them according to mean stress, right? And so the combination of these will actually come into play. Not in terms of maybe our overarching outcome, right, of which one is dominating, but rather in the details of how those numbers come together. And so this is a way to solve the problem. So I'm going to write that down here and underline it. So this is a way to solve the problem. And I've ordered it in terms of stress amplitudes decreasing. And I've associated that with the different power setting levels. I realized that for example, in the flight power setting, our mean stress is higher than for the cruise setting. So if I wanted to, I could flip these two in terms of the stresses, but keep the times the same, right? So we have to find a way to sort of slot these in such that we can combine them all into a single equation, because our elliptical model has 2 terms, and it doesn't tell us this is for this segment and this is for this segment, right? And so we sort of have to come up with a way to put them together. So this is a way to solve the problem. This is how I did it, but you could let's say, more exactly switch up the mean stresses and the amplitudes, reanalyze the problem, and see if you get a more conservative estimate. Okay, so that's my caveat at the beginning here. So if this is how we're lining it up, then we can solve this by choosing some lifetime and then seeing if we would expect failure or not. So that's how I went about this. So for this elliptical equation, that's going to be our guiding failure criterion. We can look at what we got before. So we got sort of 900 missions and 595 missions, so approximately 600 missions. So that's what I started with. I said, okay, if we're starting with the situation of 600 missions, right, because I thought it would be relatively conservative compared with what we calculated before, then I used the 2 aspects of this to come up with these ratios to then see if they would be greater than or equal to 1. Okay, so I'm going to walk through how to do that. So we can think about these 4 segments here, and we can say if our remaining life is now 600 missions, then our total number of cycles for each of these phases is 600 times whatever it was for 1 mission. So for the first 2, we only had 1, so now we have 600, 600, 3,000, and 600. Okay, so that's what we would expect if that's our remaining missions. And then what we can do is we can go to that SN curve. So I'll put an arrow here. What do we do next? We go to the SN curve and we look at what is the allowable fatigue strength or the required fatigue strength in order to get this number of total cycles for this material under high cycle fatigue. Okay. So we go to this chart here, and we only had two different numbers of cycles. So we had 600, which is going to be quite low. So if this is 100, that's 1,000, 300, 600 is going to be somewhere in here. I'm going to roughly estimate it. And if we take it across, I took it to be slightly less than 50, so I put it at 48. Okay, and then if we had 3,000 cycles to failure, that would be about halfway between 10 to the 3, 10 to the 4 on a log scale. So come up here, come across. and I'd put about 25 for that one. Okay, so that's our sigma n. Okay, so sigma n for that number of cycles was 48, 25, 48. So this is basically the allowable reversing stress. If we had zero mean stress, in order to be able to survive this number of cycles according to the SN curve. And that makes sense because it's the denominator here in our elliptical model. So we're taking whatever we have, right, our stress amplitude, and we're comparing it to that. And so we could, if we wanted to now, calculate that first term, right? So let's go ahead and do that. I did not do that in my notes, but we can do it easily. So sigma A over sigma n, and then we will square it. So for the first phase, we have 28 divided by 48. So that is approximately 0.6. Square that, we get 0.34. Okay, so that's not anywhere close to 1. And we do it for the second one. 13 divided by 48, so it's going to be even lower. So I got 0.07. Yep. Okay, and then 10 divided by 25, 0.16. And 7 divided by 48. This one's going to be very, very low. 0.02. Okay, so these are all less than half. So if these reach toward a value of 1 for the elliptical model, these are all less than half, some of them significantly so. So we would not expect this to be a huge part of anything leading to failure. Okay, so let's keep going. And now let's calculate what this creep stress is so we can compare it to the mean stress and then see if we would predict failure for any of these for a lifetime of 600 mission cycles. Okay. So we have our same 4 levels here. Flight idle, ground idle. And I'll just replicate the mean stresses here. 28, 43, 46, 43. Okay. So for this one, we're going to look more at the time. So for each of these, we had a time for a single mission cycle, which was 31 minutes, 12 minutes, 20 minutes, and 7 minutes. And so we could calculate a total time for 600 missions, which we just multiply 600 times each of those times. So we get 18,600 minutes, 7,200, 12,000, and 4,200. Okay, and then what we do is we go back to our plot for the creep stresses, and we look at the time that it takes to get a creep stress rupture, and then we compare, or we look for these times, and we look for what that stress is. So that plot was here. Find it. And I misdescribed this in the last lecture. I said this was a stress relaxation experiment. It is not a stress relaxation experiment. What it is this is many data points along here of the stress at which we would expect a stress rupture if this is held for a certain amount of time, right? So, or that was measured at a certain amount of time. So if this was at 100 hours here, then we could have a stress level that's fairly high, like 60-something PSI, right? But if we want to wait and have, and have it last, let's say, thousands of hours, then we could only apply a stress that's much lower, like around 30 KSI. So if we stay below that, we would not expect a stress rupture. Okay. So we're going to use this chart to look at the times that we had. Unfortunately, this chart is in hours. We're in minutes. So we're going to go back and translate what we had from minutes to hours so we can use the chart. Okay. So for this, we get 310. We're just basically dividing by 60. We'd already multiplied by 600, so it's just our time in minutes times 10, 120, 270. So those fall readily in the center of this chart, and so we will put our allowable stresses there. Okay, so 310 hours. So 100, 200, 310 is about right here. We're going to do a lot of like sort of chart time today. And so for that, I got 57 KSI. For 120 hours, kind of here. Oh, that's right where I drew my other line. Okay, and I got 63. For 200 hours, it's just the second line here. We get right about 60. And then for 70 hours, 10, 20, 30, 40, 50, 60, 70, go here, go across, and we get 67. So at the times that we have for 600 more mission cycles, we could, these are sort of allowable stresses before we get a rupture. Okay. So now we can go back and put those on our chart. Whoops. Okay. So if I do that, I get 57 for that one. Then we went up to 63. To 60 and to 67. And now we can calculate our mean stress divided by each of those and see what the contribution is. So I'm just going to do another column here. Mean stress, creep stress, square that. So for the first one, it is 28 over 57. Square that, we get 0.24. Second one is 43 over 63. That's the biggest ratio we've had so far. 0.47. 46 divided by 60, also high. 0.59 and 43 divided by 67. Okay, 0.41. Okay, so all these values are substantially higher than what we had before. In our table, which I did not. So the sum of those two, which we will compare to a value of 1, is 0.58. 0.54, 0.75, and 0.43. Okay, so a comment here on these values. We were checking to see if any of them went higher than 1, because that means that that power setting, that as we've identified it, would cause a failure. And so the highest one is actually the third one. And that's because it has a pretty long amount of time and less of a contribution from the fatigue portion, right? So it's only at 0.75. So when I was doing the problem, I thought, okay, well, if I want to get up to 1, let me go a longer mission cycle, right? So we had 600, but when we were doing the prediction, we found from the fatigue that it should be more like 900, right? So I did some iterations here, and I went through, and I found that we actually have to go really high in order to get anything that approaches 1. Okay. So I'm going to not go through all of those iterations. But I'm going to simplify this down and only look at that third power setting, because that's the one that's even close to reaching 1. And so if we reevaluate that third setting, and go back to here. So I'm going to reevaluate this for a high number of cycles, and it's going to be 1,500. All right, so I'm going to put it in green, and I'm going to do 1,500. That's the only thing I could do that would get it even close to 1. So I went through and I looked at all the values, and so I'm going to write in the modified or updated values in order to do this, only for the third power setting down, not for any of the other ones. And so for this one, instead of 3,000 cycles, right, we have 7,500, because it's 20 times 1,500, which means that our allowable stress drops from 25 to 20. And this new ratio is I did not put it. Let's do it. 10 divided by 20, that's half squared. So that's 0.25, I believe. Yep. Okay. So we have 0.25 here. So our damage has gone up slightly in terms of the fatigue, not by much, like 0.16 to 0.25. We're still far below 1. But that would be the modification for that first term. And if we go to the second segment, or the second aspect of this, our total time is going to change from 12,000 to 30,000. That's in minutes. And so we can take that, and if it's 1,500, that should come down to 500 hours. And then our critical stress, if we go back to that diagram and look at it, which I did not put on here, but I did put in my calculations. Oh, I do have it, never mind. Goes down to 55 here. So what this is doing is it's dropped the denominator in both of our terms in that elliptical model. So if we do that, we now get, for the second factor, we get 46 over 55 squared, nope, 0.70. So now our total is 0.95. So we're approaching 1, but we're still not at 1, and we have almost tripled the number of missions remaining. And so if we do this and we follow this elliptical model to a T, we find that our prior number of missions vastly under-predicted how many we could get according to some synergistic effect. And I went back through and I looked at this equation and I thought about it and I realized why it might be having this sort of gross difference between what we initially calculated and then what we're calculating here. And that is because of what we're using in this equation, okay? So I'm going to write the equation again on the next slide and just have some commentary about it. So the first term was stress amplitude divided by fatigue strength squared. Second term is the mean stress divided by the creep stress squared. So that was our failure criterion. And the first term, when we did our initial analysis and we found a value of n equal 900 additional missions, we followed the very standard procedures, not complicated, high cycle fatigue. So I had a high confidence in that value. And when I went back and I looked at how we calculated this phenomenon, not necessarily this particular term today, but the phenomenon before where we got 595 cycles. Let me just turn, yeah. We calculated that not using the mean stress. And we did that because we were not thinking about any sort of cyclic nature. We were only thinking about the timing of things. And in this problem, when we are sitting at those levels, right? So if I go back and I sort of draw what we had, it was like something like this, you know, and then it went back down. But when it gave us this number of minutes at each power level, that had nothing to do with what was cycling at the time. It was just a number of minutes at that stress. And so I did not want to use mean stress to calculate that because I didn't think it was appropriate. These cycles that are happening are on the order of minutes, but the changes between them are relatively instantaneous compared to the time that they're sitting at each level. And so that's why there's such a big discrepancy between this failure criterion, which when combined gave us something like n equals 1,500 or greater than 1,500 mission cycles remaining, is because we used the mean stress instead of the maximum stress. On that diagram of, nope, it must have been after, hang on. Yeah, on this diagram here. And so if we think about that, then using that maximum stress and thinking about time, we're going to get a much more conservative value. We also, oops, go back. Okay, so that's one reason for the big discrepancy, is using the actual nominal stress that we were given at each level versus using a mean stress. And that goes hand in hand with the reliance on syncing up, right? So we had to sync up two different phenomena into a single equation, right? And so that was also not a straightforward process. And we could have done that differently. So those are the two reasons why we got vastly different numbers of remaining cycles. If I had to give a recommendation as to how to get a better one and take into consideration this synergistic effect, I would say we have to run this sort of two different ways, right? So I ran it where I synced up the power, what they call like power settings, with the amplitude of each sort of reversing stress cycle because I needed a way to anchor them together. So that's one way to do it. That way is more accurate for the fatigue, right? Because I said it's more extreme when we have higher amplitudes, and amplitudes is what we care about when we care about high cycle fatigue. If we change the way that we align it in the beginning, and we, instead of doing power settings with the amplitude, if we keep the power settings and we look at the time at each one, and then associate the time with the power amplitudes instead, like, okay, I want to have the most extreme case, highest stress amplitude and the longest time, right? That would have more of an emphasis on the creep aspect, or more of an accurate, let's say, representation of the creep aspect, right? And so these are the problems that we have when we try to assign a failure criterion for a complex situation. Okay, so my best advice would be to solve it with one systematic way, and then solve it when you have more extreme, where you're taking the maximum of time and the maximum of these amplitudes and sort of putting those together, even though they don't exactly match up in either way. And that will give you the most conservative number of remaining missions, right? And so you can tell your boss sort of at a minimum, we would get that number of missions left with a combined creep and fatigue analysis. If we look back and think about the partitioning of these effects, so we can do it on this slide. And if I can write down, let me go back here, 0.34, 0.07, so 0.34, 0.07. These were the ones from the very first round. 0.16, 0.02. So that's the first term, sigma A, sigma n squared. And then this one went up to 0.25. Okay. We can see that the magnitudes generally of the first column are less than those in the second column, with the exception of the first row here, right? So to answer part D of this question, which was, which one of these effects dominates the design situation, that's what they called it, I would say in the way that we have analyzed it, the way that we've lined it up, and that we've used the mean stress, then the terms generally for the creep would dominate. So that would be my answer with all of those caveats. If we, instead of using the mean stress, as was recommended, if we put in the maximum stress there, then we also find that the creep aspect dominates. Okay. And I would say I tried to do this analysis where the fatigue was more accurate. So if fatigue is more accurate, but also always lower, then that's a pretty good idea that it's less influential in the problem. If we realign the segments, reanalyze the problem, we may find that there is more of a balance between the creep and fatigue. And so I'm going to leave that as an exercise for you if you want to do it. But this is the sort of the overall answer to this example problem. Okay, so there is no sort of one right answer, but there are better and worse ways to go about it, and I've chosen one sort of in the middle here. So there's 2 people with us today in class. Do you all have any questions before I wrap up? No. Okay. Yeah. So this was a lot of commentary and just working through this problem. And so I am going to end the lecture portion there for today and just give some general comments about the class sort of bookkeeping things. Point number 1 is I did not weave in enough journal article reading, analysis, or critique in order to really give an assignment. So I'm not going to have that assignment because we do not have the resources to do it. So because of that, there is some number of points associated with that assignment, which now do not have something associated with them. And so what I think I'm going to do is distribute those points among the other assignments, and then make a journal critique assignment as like optional extra credit, because I know there are some people in the class who really want that. So I will make an announcement about that either today or on Monday, so that everybody is clear about that. And then the only remaining assignments are problem set 5, which is due next week early, and then the final exam, which will be another take-home exam. I am almost done grading exam 2, and so I hope to, by this weekend, have those grades in, and then the grader will start grading problem set 5 as soon as he gets it next week, because he has all the solutions and the rubrics and stuff. And so that is kind of how we're going to wrap up the class. I would encourage you to fill out the evaluation that you are provided through the university, and to take into consideration every sort of part of the class. So I guess the topics that have been covered, the way you feel that they were covered, how the assignments treated them, etc. And those numbers and those feedbacks that you provide are not just sort of like a subscribe and like on YouTube. They don't just count for some sort of number. I actually read the comments, and the numbers go into my permanent record as a faculty member. So please do be thoughtful if you do fill that out. And that's my only ask, and we can wrap it up there. There's one more lecture on Tuesday, and yeah, then we'll be wrapping up the class. So thanks so much.